Hello everybody. Today I'm gonna discuss power factor correction method. So here you can see that this is an inductive load, and let me select the pencil cursor. Yeah, this is the inductive load, and this is the total kVA rating, and this is working power, and this is the reactive power. So our aim is to reduce the working power as well as reducing the kilowatt, I mean the reactive power. So capacitor is the best way to use in parallel with this load. So the inductive power is happen mainly due to the the power factor is lagging happen due to the inductive nature. So if we connect parallel capacitor in with inductive load, then the power factor will be improved. Later on we will show how it's gonna improve. Now let's go to the next slide. Here we see this is the power triangle. So this is, we already know, this is the active power, P equal to VI cos theta, and this is the vertical component is the reactive power, whereas this is the apparent power. This, so according to the formula, this is kVA square equals real power square and kilovolt powers, and the power factor cos theta can be defined as power factor is the cosine angle between voltage and current, and as well as the horizontal component. Horizontal component is active power is VI cos theta. This is actually watt, or we can write kilowatt. This is kilohertz, and this is volt ampere. So there is no cos theta here, and this is kilowatt, I mean it's P, this is Q. Yeah, here is P real power, this is Q reactive power, this is S is called apparent power. So cos theta equals kilowatt divided by kVA. So here is the expression of power, and this is the power triangle for lagging power factor. So it's just like a Z equals R JXL. So if we draw the phasor diagram, this is the R, I mean that is equivalent to real power, and this is the XL, and this is Z, and this is the theta power factor angle. So for the capacitive load, if we write here Z equal R minus JXC, then how can we draw? This is R, this is XC because of negative sign here, and this is Z, and here is the power factor angles theta. So it's just similar to this. Let's see an illustration here. So what we can see here, suppose a circuit draws a current of 10 ampere. So I equals 10 ampere and the voltage of 200 volt, and power factor is 0.8 lagging. So it's a inductive load, obviously, because of power factor lagging, as we say. So if the circuit is inductive, then the power factor is lagging, and on the other hand, when the load is capacitive, so the power factor is leading because the current leads to voltage. So the nature is usually defined by the current. So when current is lagging, we call it power factor. Why the current is, we denote the power factor whether it's lagging or leading is denoted by current, because in our household or any official or any building, so all the load are connected in parallel. So in parallel we know that voltage remains same, so voltage we should take as a reference. So what is remain? Only the current, because power is dependent on voltage and current. So power will come later after voltage and current. So if the voltage remains same for the all connected parallel load, then the nature of current will be varied. So for the inductive load, we know that the for the inductive load. If this is inductive, then this is voltage and the current is lagging. So this is the power factor angle. For the capacitive load, voltage remains same. Here you see that it remains same as a reference and the current is leading. So voltage actually is the reference for the parallel connected load. Okay, so now here we have to find the apparent power. So apparent power is VI, or it can be written as over here like watt squared then bar square. So if we do this, we'll get the same answer. So active power is bi cos theta. So bi cos theta, and this is bi sin theta. Sin theta, we know the value of cos theta. We can easily determine the value of sin theta. It's 1 minus cos squared theta over half. So here we can see, like, for DC power. So for the DC circuit, if there is no power factor is mentioned, what we can write for the power equation? P equals VI. So this is the apparent power, and the real power for the DC circuit remains same. So it should be in watt for the DC circuit. Is for, if it is DC, then the unit would be watt, and it's 2000 here. So, but in AC, what we get, the active power is 1600 watt. So for the DC, there is a 2000 watt. So what's the difference? Because this difference is the here, the power factor, because all the power is not the active, not the useful power. So there is some wasted power. So where is the wasted power goes? So here, this is the reactive power, this is the reactive component. So what it actually does, so it's just a back and forth. Here is mentioned that the reactive power 1200 bar is not a useful work. So here there is a graphical illustration here. So like it's a bottle of a beer. So this is real power, this is full of beer, so it's a watt, and this is the useless, I mean the wasted electricity is mentioned here. This is a kVA, and the total is kVA. For the DC circuit, this kVA is equals to kilowatt. So what we actually want to do, our objective is to getting more more active power or real power here. So we need to reduce this kilovolt amperes. We need to reduce this one. So if we increase the amount of beer here, then we'll get more beer. So how can we reduce this kVA rating? So the most common way is using the capacitor. So capacitor gives the negative reactive power that's minimize this portion. Let's see how it does. So before going to the power factor improvement, we will discuss the impact of power factor on several point of views. So for the three-phase circuit, it's a for the three-phase circuit, so P equals root 3 pi cos theta, all of the line value, and if we write in the phase value, I shall write P three phase voltage, phase current, and cos theta. So we can see that the power factor cos theta is inversely related to load current. So if it is low, then load current will be higher. So what happens if the load current is higher? Let's see. So here I'm gonna discuss some the effect of low power factor. So first one is a large kVA rating. So we know all the equipment, particularly alternator, transformer, and the protective element like switch gear, always defined in kVA. So we know from the power triangle, it's here is the power triangle. It's S, it's P, and it's Q. So and it's theta. So cos theta equals P P divided, here it is S. So if the power factor is low, then the kVA rating will be higher. So if the kVA rating is higher, it means that the manufacturer must need to build a higher, it's a bigger device, because for the large kVA rating, the equipment size must be bigger. So it's a disadvantage if the power factor is gonna low. So our objective, I said in earlier, is to how to increase the power factor as well as to reduce the kilovolt ampere power, I mean the reactive power, and to increase the real power. So here is another impacts, greater conductor size. Let's see how it's happened. So we see that, so to transmit the same amount of power at the constant voltage, the conductor will have to carry more current at low power factor. Let's see how. For instance, AC motor, single phase AC motor, is an inductive load. So it's a 10 kilowatt load and the voltage is 250 volt. This is the line voltage. So at unity power factor, when the power factor is 1, here the power factor is 1, then how is right? We can write so okay, this is kilowatt, I mean volt ampere divided by volt, then we'll get the ampere. This we'll get 40 ampere. And if the power factor is reduced, because what we write here, this is P equals Bi cos theta, so I equals P, here P is 10 kilowatt divided V is 250 into cos theta here 1. So we get 40 ampere current here. But if the power factor is reduced to 0.8, what will be the value? Just put the value over here. 1 is replaced by 0.8 and we'll get the current is 50 ampere. So what we see, if the power factor is reduced, then the carrying current is greater. So if we need to carry this higher current, so the conductor should be thicker. So here is the another disadvantage, because for the thicker conductor, there is a much power loss is there and the cost is higher. And another disadvantage is large copper loss, as we see in the above. So if power factor is lower, then the load current will be higher. So if the load current is higher, then the copper loss I square R would be higher. So this results in poor efficiency. So always our objective is to reduce the these losses, I square R losses. So how can we reduce? We have to reduce I. So how can we reduce I? So definitely we have to increase the cos theta. And the last one is voltage regulation. So if the conductor is carrying the higher ampere rating current, higher ampere, then there is a loss happen, I mean the voltage drop occur in the conductor. So as we see in the transmission line, like let me draw, is the source in, and here is R, is L, and here is the load. A simple circuit. In earlier we showed that this is Vs, this is receiving end voltage, this is Vr, and this is in series, this is I, this is Z. So if I is higher, then the voltage drop. This is the voltage drop. Voltage drop is defined as Vs equals Vr jog Iz. If I is higher, this is the voltage drop. This is the voltage drop, sorry. This is the voltage drop, and if I is higher, then the voltage drop would be higher and we'll get the less amount of voltage at the load end. So it causes the results the higher voltage drop as well as the poor voltage regulation. Now how now this is, we will discuss the power factor improvement, how it can be happen. As we said, if we connected capacitor in parallel to the inductive load. Here is the inductive load, no capacitor is added. So if we added capacitor in parallel to the inductive load, then the power factor will improve. Now we'll show in mathematically how it's going to improve. Here the this voltages remains same because in parallel the voltage remains same. So the current through the load is defined as I. So if the capacitor is connected in parallel, let the current over here is IC and the total current is I prime. So now let's see how to draw the voltage, the phasor diagram. Here is the reference is V. So for this circuit, how can I draw? This is V and this is I, this is theta 1. Okay, now if I add the capacitor is here, we know the capacitor for the capacitive the current is leading. Here if I add the capacitor over here, it's leading, it's a pure capacitor actually. So now what will be the I prime? I prime is the resultant of I and IC because it's divided here and here. So what is the resultant? The resultant will be lies in between these two, I and IC. So here the resultant one, this is I prime. Yeah, here this is I prime. If we put a dotted line here, then we'll get this is the resultant one. And note that this current is never here because you see according to phasor diagram this magnitude is lower and this is higher and it will never cross that angle. On the other hand, there is another reason because power factor its maximum value could be 1. Maximum value could be 1. So when it will be maximum, when theta equals 0, then power factor equals 1. So theta equals 0 means voltage and this current remains in the same line. When the I prime is here, then theta equals 0. So there is no way to go this I prime above the voltage line. So this is the curve. So in previously the angle is cos theta 1, whereas phi 1 is greater than phi 2. So if for the this is the power factor initially cos theta 1, as the angle is higher then the cos theta value is lower, and then the cos theta here, this is theta 2. Here we see that for adding the capacitor we'll get a new current over here. So this is the improvement actually. So when there is no capacitor, the current is lagging this point, and if we add this capacitor, this is the current level is up to the here. So our objective, how can it close to the voltage, because the power factor angle will be closer to the voltage, and we see the power factor is getting improved. Here it's improved through adding the capacitor. This is the all happen because of this capacitor, thanks to capacitor. And this is the current expression, like here is a triangle. So this component is I sine theta 1, this component is I sine theta 1 because this is I line here, and this component is this component is I prime sine phi 2 or theta 2. And so sorry that's my bad. Yeah, this this component would be I prime sine theta 2, and this one is improved due to IC. So what I can write? I can write this is IC plus this is the I prime sine theta 2 equals the whole one equal I sine theta 1. This is I sine theta 1. Yeah, so this is the expression for capacitive current, how much current is supplied by the capacitor. And the value of capacitor it can be determined easily. So capacitor, this is a power factor improvement from cos theta 1 to cos theta 2. So yeah, theta 2 is the lower, so it's improved to cos theta 2 as we said here. And we know Xc equals Xc, I mean the reactive capacitance of V by Ic, and Xc we can be written as 1 by j omega c. Here is the imaginary term is omitted, and then we can write Ic equals C equals, here you just consider this C equals Ic divided by omega is the angular frequency is 2 pi f, omega is 2 pi f, and this is the line voltage, and this is the capacitive current, and this is the value of capacitance. Now how much kVAr is reduced, I mean supplied by the power factor correction equipment means the capacitor. So it just means the capacitor. So how much the leading kVAr, as we say in the above, our objective is to reduce this portion, and we'll get the more BR over here. So how we're gonna achieve this using a capacitor? Now we have to find what's the improvement. So from the figure we see that this portion is due to IC, this one, this dashed line, this is for the capacitive component. So here is the total kVAr, so this is the leading kVAr supplied by the capacitor. As we saw, this is the lower portion, this is for the capacitor, yeah, and this one exists from the circuit. This is the previous one, this is the previous kVA rating, and kilowatt remains same, and this is the new kVA. So how can you get this? This is the improvement. The improvement is the BC equals the big one AB minus AC kVAr, and according to the formula tan theta, we know tan theta is kilowatt divided by kVA. So tan theta equal to kVAr divided by kilowatt. So if we put this formula over here, we'll get this. Now let's see some example here. If an alternator supplying a load 300 kilowatt, so P is given here. This is a P is 300 kilowatt. This is 300. Power factor is 0.6, and then if the power factor is raised to unity, if this is theta 1 and cos theta 2 equals 1, then how many kilowatts? Here for 0.6, the alternator is giving 300 kilowatt, and now for the same kVA loading, if the power factor is raised to 1, then how much power it will be supplied by the alternator? Let's see. kVA, we have to find the kVA for 0.6. This is the 500 kVA. So for the same kVA rating, what do you get? For 500 kVA rating, the power is 300 kilowatt, and similarly, if we write the formula over here, right, like here, what is the formula? Cos theta equals kilowatt divided by kVA. So now kilowatt is equal to cos theta. Now the cos theta 2, what is the value? 1 into kVA for the same kVA loading. yeah, kVA is a 500, so we'll get 500 kilowatt. Here's a 500 kilowatt. So when the power factor is increased to 1 from zero point 0.6, the increased power supplied by the alternator is 200 additional. So we see that if the power factor is improved, then we'll get the real power is more. And the next example, here it's a three-phase 5 kilowatt induction motor. It's a load in the motor is always load, and the power factor is 0.75. A bank of capacitor is connected to the delta. Yeah, so there is a three-phase, so there is a mesh connection is here. So, and for the adding the capacitor and all the branches, the power factor is leading to 0.9. Now we have to determine the kVA rating supplied by the capacitor in each phase. So we know the formula here. This is the leading kVA supplied. This is the P, tan theta 1, tan theta 2. We have cos theta 1, then we can find theta 1 and theta 2, and then tan theta 1, tan theta 2, and the value of P is here 5 kilowatt. And if we put here, then we'll get the total. This is condenser bank, means when all the capacitor is connected in the three-phase 3 arms, then it's called the condenser. And then we'll get the kVA rating is by 3 capacitor is this, but we have to find for the each phase, just divide by 3, we'll get this. So each capacitor will contribute 0.663 kilovolt ampere. And yeah, that's it. And I will left some example for your homework so that you can understand. So these two the example are done here. So these two examples for your homework. So please let me know if you face any problem. Feel free to contact with me. So thank you everybody. Have a good day.